Okay, the masked professor is on the air once more. One second. There, that should make things a bit easier for you, the audience at home, or wherever you may be. Over the bright blue sea comes Sir Joseph Porter, KCB, as the old song reminds us. All right, so as you may have guessed, today's lecture is on Inspection Technologies, Chapter 22, and today is October the 26th. Wink, wink. All right, so in this chapter we will discuss inspection metrology, conventional measuring and gauging techniques, coordinate measuring machines, surface measurement, machine vision, other optical inspection techniques, and non-contact, non-optical inspection technologies. Inspection metrology. First of all, we define measurement as a procedure in which an unknown quantity is compared to a known standard using an accepted and consistent system of units. So, measurement is the means by which inspection by variables is accomplished. Metrology we define as the science of measurement. It is concerned with 7 basic quantities: length, mass, electric current, temperature, luminous intensity, time, and matter. And from all of these basic quantities, the other physical quantities are derived. So, the characteristics of measuring instruments. First of all, there's accuracy. How closely our measured values agree with the true value. Second, we have precision. That is a measure of the repeatability of the measurement process. And we have the rule of 10, that the measuring instrument must be 10 times more precise than the specified tolerance. We define resolution as the smallest variation of the variable that can be detected. Our speed of response is how long the instrument takes to measure the variable. There are other things that we may be concerned with, such as the operating range, reliability, and, of course, always the cost. All right, so very often there is confusion surrounding accuracy and precision. Often people think of them as being the same thing when in fact they are not. So in illustration A here, we have very high accuracy right? The mean of our instrument is co-located with the true value, but we have a large variance, and so the distribution of our measurements may be off. In illustration B, we have low accuracy but high precision. So our distribution of measurements is quite narrow, and we have the mean of where those measurements fall here, but it is not very close to our true value. And then in C, we have high accuracy and high precision. Here, the true value and the mean are very close together, and we have a very small variance, allowing us to say this has high precision. We still often use analog instruments versus digital instruments to measure variables. An analog measuring instrument, our output signal varies continuously with the variable being measured. So the output signal can be any of an infinite number of possible values over the operating range of the instrument. Whereas with a digital measuring instrument, it can only assume any of a number of incremental values that correspond to the variable being measured. So our number of output values is finite, but it has the advantage that it's easy to read the instrument and it's easy to interface to a computer. When we're talking about inspection, we have two basic types of inspection techniques. The first of these is contact inspection. In other words, it makes contact with the object being inspected. The second, strangely enough, is non-contact inspection, where it does not make contact with the object being inspected. So when we talk about contact inspection techniques, we use a mechanical probe that makes contact with the object being measured or gauged. The principal techniques that are used are conventional measurement and gauging instruments. Those might be manual or they might be automated. Coordinate measuring machines, or CMMs. Stylus type surface texture measuring machines. And we'll talk about how those work a little bit later. When we're talking about non-contact inspection techniques, we're using a sensor or a probe that is located at a certain distance away from the object that is being measured or gauged. We have two categories within that. Optical, where we use light to accomplish the inspection, and non-optical, where we use energy in another form other than light. The advantages of non-contact inspection: well, we avoid any possible damage to the surface of the object. it is inherently faster than contact inspection. We can often accomplish that in the production line or in production without having to do additional part handling. And it gives us an increased opportunity for 100% inspection. All right, so here is a parts versus quantity chart for inspection technologies. At the lowest part variety, lowest parts quantity, we have manual measurement and gauging. At a slightly higher parts quantity, we have manual and semi-automatic measurement and gauging. And then at the highest end of the parts quantity, we have dedicated automatic measurement or machine vision. At a slightly higher parts variety, we have our but yet a low parts quantity. We have motor-driven and manual coordinate measuring machines. Right? That then implies that flexible inspection systems are used at a slightly higher parts quantity. And at the highest level of parts variety, we have direct computer-controlled coordinate measuring machines. Okay, so as you can see, the coordinate measuring machines kind of blend from one parts variety to the other here. All right, when we're talking about conventional measuring and gauging techniques, we are using measuring instruments that provide us a quantitative value of our part feature of interest. So some examples of this would be steel rules, calipers, micrometers, dial indicators, or protractors. Right? Obviously, we have different levels of resolution on these different types of measurement instruments. For gauges, they determine whether a part feature falls within a certain acceptable range. So very often a gauge will just be a simple go, no-go gauge. Some examples are snap gauges for external dimensions, plug gauges for hole diameters, or thread gauges. Okay, so easy enough. All right, so when we talk about coordinate metrology, in that case, we are going to be concerned with the measurement of the actual shape and dimensions of an object and compare these with our desired shape and dimensions specified in the part drawing. Very often we use coordinate measuring machines, or CMMs. That's an electromechanical system designed to perform coordinate metrology. A coordinate measuring machine consists of a contact probe that can be positioned in 3D space relative to work part features and the XYZ coordinates can be displayed and recorded to obtain dimensional data about geometry. Oh boy. All right, so here we see a coordinate measuring machine, and this is a very typical type that we see in industry. So this gantry can move back and forth in the X direction. The probe and its supporting structure can move back and forth in the Y direction. And the probe can be moved up and down in the Z direction. Okay, so we have a probe head and a probe. Typically, the probe has a ruby bead on the end or some other material that's not easily deformable. Very often this works together with a computer system that records the measurements made by the coordinate measuring machine. So the coordinate measuring machine components, we have a probe head and a probe to contact the work part surfaces. We have a mechanical structure that provides the motion of the probe in the X, Y, and Z axes, and displacement transducers that measure the coordinate values on each axis. So the probe doesn't just crash into a part, it can be deflected, and that is measured. Some optional components that we may have on many coordinate measuring machines. We may have a drive system and a control unit to move each different axis. We may have a digital computer system that has application software to guide the coordinate measuring machine. All right, so these contact probes come in single tip and multiple tip type probes. We have the probe head, and then we have the probe itself that fits into the probe head. It comes down, and we have a ruby ball on the tip of the probe. All right, so the mechanical structure of a coordinate measuring machine comes in 6 common types. First is the cantilever type. Second is the moving bridge type. 3 is the fixed bridge type. 4 is the horizontal arm type. 5 is the gantry type. And 6 is the column type. Now, does it have to be in that order? No. All right, so here we see 2 types of coordinate measuring machine structures. Here we have the cantilever type. The machine is free to move here in the x-axis. It can the probe can move back and forth in the y-axis and up and down in the z-axis. Here we have the moving bridge structure, and so the whole bridge can move in the X direction, then the probe structure can move in the Y direction and up and down in the Z direction. Here we see a fixed bridge coordinate measuring machine type structure. In this case, the probe head can move in the Y direction and in the Z direction, but we actually have a table that moves our objects in the X direction. And then we have a horizontal arm, also called a moving ram type, where we have the structure moving in the X direction. The probe arm moves in the Z direction and the Y direction. Here we see a gantry type of coordinate measuring machine where we have movement in the X direction by the gantry on the two support structures. The probe head and the probe are free to move in the Y direction and the Z direction. And here we see the column type of coordinate measuring machine where the probe head and the probe only move in the Z direction, and a table on the machine actually moves in both the X and the Y directions. All right, so when we talk about our coordinate measuring machines, they come in four categories. One is the manual drive coordinate measuring machine. In that one, the human operator physically moves the probe and records X, Y, Z data. Although I want to say I've seen the type where the human is moving it and yet it's still recorded by a computer. We can have manual drive and computer-assisted data processing. Oh, perhaps this is what I was talking about. So that it can perform calculations assessing the part features. We can have the motor-driven coordinate measuring machine with computer-assisted data processing. In this case, we use a joystick to actuate the electric motors to drive the probe. And finally, we have the direct computer control, or DCC. It operates like a computer numerical controlled machine tool, and it requires a part program as part of its software. When we talk about the direct computer control, first of all, we can have the manual lead-through type. We talked about this with robots, where the operator leads the coordinate measuring machine probe through the various motions in the inspection sequence, indicating the points and surfaces that are measured and recording these into the control memory. All right, so that is pretty quick and easy to program. We can also do offline programming, where the program will include motion commands, measurement commands, and report formatting commands, and is prepared offline, very much like a CNC program. the coordinate measuring machine software, we have a set of programs and procedures that we use to operate the coordinate measuring machine and its associated equipment. So, for example, we might have part programming software for direct computer control machines. Other software we divide into these three categories. Core software other than direct computer control programming, post-inspection software, and reverse engineering and application-specific software. Our core software that is other than the direct computer control programming. These are the minimum basic programs for the coordinate measuring machine to function. And this applies only to direct computer control machines. Some examples might be probe calibration. We want to define the probe parameters so that our coordinate measuring machine can automatically compensate for the probe dimensions. We have the part coordinate system definition so that we don't have to align the part with the coordinate measuring machine axes. The axes are instead aligned to our part. We have geometric feature construction. For example, a hole center. And tolerance analysis will compare the measurements with the part drawing dimensions and tolerance to see if a part is in tolerance or out of tolerance. Post-inspection software, these are programs that are applied after our inspection procedure. So we use statistical analysis as a software which tells us our process capability and our statistical process control. We have graphical data representation displaying our data collected during our coordinate measuring machine inspection in a graphic or pictorial way that gives us an easier way of visualizing any form errors and other data that might be relevant. We might have reverse engineering and application-specific software. Reverse engineering, our coordinate measuring machine will explore the part surface and construct a 3D model of that part. Application-specific software might do gear checking, thread checking, cam checking, or automobile body checking. Right? And I'm sure that this is only limited by the imagination of the software designers. So, the advantages of using coordinate measuring machines over manual inspection Well, first is a reduced inspection cycle time. That gives us a higher throughput rate. It's noted that this is especially with the direct computer control, where we can achieve 90% reduction in certain tasks. Greater flexibility. Coordinate measuring machines are general purpose machines. Reduced operator errors in the measurement and setup, always something that we want. A greater inherent accuracy and precision, also something that we want, of course. We can avoid multiple setups, so we can do all the measurements of a part in one setup. Now we can also have inspection probes on machine tools. These can be mounted on the tool holders, stored in the tool drum, and they can be handled by our automatic tool changer in the same way that cutting tools are handled. So we insert them into the machine tool spindle with the automatic tool changer. So when it's mounted in the spindle, the machine tool is controlled like a coordinate measuring machine. The sensors in the probe determine when contact is made with the part surface, and then our required data processing is performed, and it interprets the sensor signal. We can also have portable coordinate measuring machines. So conventionally, when we use a coordinate measuring machine, we have to remove the parts from the production machine, take them to the inspection department where the coordinate measuring machine is located. New coordinate measuring devices will allow those inspection procedures to be performed at the site where the parts are made. So examples given are a Faro gauge, also known as a personal coordinate measuring machine. It has a 6-jointed articulated arm. At the end of that arm is a touch probe to perform coordinate measurements similar to a coordinate measuring machine. All right, so here's an illustration of a Faro gauge, and you can see it has many joints to allow it great flexibility in measuring a part. B shows a Z-cat. I'm less familiar with this type, but it allows rotation around a T-joint. We have a probe tip, and we can move in the X and Z directions. Okay, of course we have advantages to being able to do in situ inspection. The necessity to move those parts from the machine tool to the CMM and back is eliminated. So that way our material handling is reduced. Our inspection results are immediately known. Our machinist who is making the part also performs the inspection. And because the part stays attached to the machine tool during the inspection, our datum reference locations that have been established on the machine tool aren't lost. So, any further machining still uses those same references, and we don't need to refixture the part. Well, surface measurement, of course, is very vital in certain types of parts. So, most surface measuring devices use a contacting stylus. Therefore, that is contact inspection. This is often a cone-shaped diamond stylus with a point radius equal to 0.005 millimeters, which is approximately 0.0002 of an inch, and a 90-degree tip angle. So, as the stylus is traversed across the surface, the tip also moves vertically following the surface topography. The movement is converted to an electronic signal that can be displayed as either the profile of the surface or the average roughness value of the surface. All right, so here is showing the stylus type of surface measurement, right? So we have a vertical motion in our stylus. We have a traversing direction. We have a stylus head, and here's our workpiece. What this does is it records deviations from a nominal surface. So we have an XY graph where Y are our deviations from the actual smoothness of the surface. So this is displayed as a profile of the surface that has been indicated by the stylus trace, or as the average of the surface deviations during the trace. Okay, so when we talk about the area surface measurement, a limitation of our stylus type instruments is that the surface is measured along a line traversed by the stylus. It is therefore a 2D or profile measurement. Using optical metrology is our best approach to achieve the area surface measurement. That way it's non-contact. We can have scanning line lasers that give us a 3D colored hologram of the surface. And it consists of millions of data points. Machine vision means that we have acquisition of image data followed by processing and interpretation of these data by the computer for some useful application. Okay, Sometimes we call that computer vision. This may be a 2D vision system that gives us a two-dimensional image. That is adequate for many applications. If we're inspecting flat surfaces or presence or absence of components. To obtain a 3D vision system, to get our three-dimensional image, we have to have structured light or two cameras so that we have that contrast. So here we see how a machine vision system works. We have our camera and we have light source. The light source is focused on the parts. The camera is recording. That image is digitized. Then the image is processed and analyzed. Then it is interpreted, and we make decisions or take action based on that interpretation. So, with that image acquisition and digitization, so we have the camera focused on the subject part. Our viewing area is divided into a matrix of our picture elements, or pixels. So each pixel is going to have a value proportional to the light intensity of the portion of the scene and is converted to its digital equivalent by an analog to digital converter. If we have a binary system, the light intensity is reduced to an on-off kind of system where it's either white or it's black. In a grayscale system, we may have multiple light intensities that can be distinguished. Remembering, of course, the absolute judgment limits inherent in human factors. Each frame is stored in a frame buffer, in other words, computer memory, and refreshed 30 times per second. Okay, so we should be able to get a decent shot. All right, so here we see dividing our image into a matrix of pixels. Here we have our part on a table. We have a matrix that is imposed on that scene, and then pixel intensity values are recorded in black and white for the scene. Right now, obviously, this is a very crude representation, and the actual values would be broken down further and further and further until we could distinguish features like the hole would not just show up as 4 black spots. The illumination techniques that we may be using would be front lighting, where the camera and the light sources are on the same, are all from the same side. Backlighting, where the light source is below the part and the camera is above. Or side lighting, where our light sources are way offset in angle compared to the camera. some more illumination techniques we might use. We might use our structured lighting where we have a planar sheet of light. The light source comes from the side, but again, it's a sheet of light. The camera is then interpreting that to see what is the deviation from the straight line of the sheet of light. We might have strobe lighting where our light amplitude, we actually have a pulse of light, right? So we see that here over time. The camera is actuated during the pulse of light, and that is timed so that the pulse of light hits the part and the camera sees the part. All right, so when we talk about image processing and the analysis of those images, first of all, we have segmentation. These are techniques to define and separate regions of interest in the image. So this may be done by thresholding, where we're converting each pixel to a binary value so that it's either white or black, and comparing the intensity level to defined threshold values. We might have edge detection, which determines the location of our boundaries between an object and its background. So we're using the contrast in the light intensity between adjacent pixels at the boundary of an object. We use these to get feature extraction, where we are determining an object's features such as the length, the area, the aspect ratio. When we're thinking of interpretation, so our image has to be interpreted based on the extracted features. So we are concerned with recognizing the object using pattern recognition. So common techniques within that are template matching. It compares one or more features of the object image with the template, the model that's stored in its memory. Or feature weighting, where we combine several features into one measure by weighting each feature according to its relative importance in identifying the object. All right, so when we talk about the applications that we can use machine vision for, well, a big area, of course, is inspection. Dimensional measurement, dimensional gauging, verifying the presence or the absence of components in an assembly, verifying the hole locations or the number of holes, or detection of flaws in printed labels. All right. We can also use machine vision for identification, for when we want to sort parts or count parts, also for visual guidance and control. So that's for bin picking, seam tracking in continuous arc welding, or part positioning. Of course, we have some other optical inspection methods. Conventional optical instruments. First of all, we have the optical comparator. This is an old technology, but still a good one. Oops. Conventional microscope, obviously also an old technology. We have scanning laser systems, linear array devices, and we have optical triangulation techniques. The scanning laser device, we have a laser. It is shooting onto a rotating mirror, going through a collimating lens. The part is here in between, and then we have a collecting lens that all goes into a photo detector. And then that information goes to a signal processing microprocessor, and our output is whether or not the part is the right size. A linear array measuring device, we have our planar light sheet. We have an object here that we are measuring, and a linear photodiode array. With optical triangulation, we are shooting a light at the object. We use a linear photodiode array or some other kind of photo detector. So we want to measure the range R here. Our length L and our angle A are both fixed, and we know what those are. So our R can be determined from the trigonometric relationship R equals L times cotangent A. All right, so we also have non-contact and non-optical inspection techniques. We can use electrical field techniques such as reluctance, capacitance, and inductance. Radiation techniques such as X-ray radiation, ultrasonic inspection techniques, which work similarly to radiation, only we're using a reflected sound pattern from the test part and comparing that with the standard. The parts must be presented in the same position and orientation relative to the probe using this technique. And of course, we remind you that this work is copyright, so don't even think about stealing it. No, sorry, just kidding. All right, well, that wraps up our lecture for October the 26th. And I will see you again on Wednesday, October the 28th.
And